Hello everyone and welcome to the Undergraduate's Guide for Capacitance. In this video we're going to be going over the basic equations of capacitance, what dielectrics are and how they affect capacitance, and finish off with kind of a complex example of capacitance through that of a coaxial cable. For the equations, we start off with our basic relationship and how capacitance is given through the charge and the voltage. The next relationship is for parallel plate capacitors, and that is epsilon, which is known as permittivity, times the surface area divided by the distance between these two capacitors. And we're going to be deriving this equation in a little bit. The next couple of pieces of information are needed for this derivation and also just helpful relationships to know in general. The electric field is known as something called D over epsilon, and to reverse this, it could be D equals E times epsilon, and that is one of the ways to write Gauss's law. It's just a way to group E and epsilon together fairly simply. And epsilon, you'll see epsilon sub r and epsilon sub naught. Epsilon sub naught is this constant right here, the permittivity constant. It's very helpful to remember this as it shows up pretty frequently. And this epsilon sub r is given as a whole number or a number in general based off of what your dielectric is made out of. So for deriving this equation, we have to start off with our parallel plate capacitor that has charge Q and minus Q respectively, a set distance D apart, and a surface area capital S. We start off with our basic relationship, and we find that voltage is the integral of the electric field over a distance. In this case, we denote that as capital E times that distance D. In order to find this E, we have to use Gauss's law, and that is finding the electric field through a surface area. And that is equal to the enclosed charge over the permittivity. And going further, this E dot ds is just E times S because the dot product goes away. There's no cosine, or the cosine is of 0, which is equal 1 because the electric field is going in the same direction as that normal of the surface area. And that's equal to the charge over the permittivity, and bringing the S over, we have the electric field is equal to Q over capital S times that permittivity. Then we can take our voltage, plug that E into here, and we come down here and we get voltage is equal to the charge times the distance over the permittivity times the surface area. And finally, plugging that into the capacitance equation, we find that the Q's cancel out, and we're left with the capacitance is equal to the permittivity times the surface area divided by the distance. So what exactly is a dielectric? Well, a dielectric is an object you place in between both plates of the capacitor. And essentially what happens is this line of charges on this plate will pull the opposing charge from the dielectric towards that area, and the opposite happens on this end. What this causes is a drop in voltage because the potential is decreased across this gap. And if we look at our basic capacitance relationship, if the voltage decreases, the capacitance will increase overall. And this is kind of shown through the permittivity of the object. A permittivity is a physical constraint or a physical attribute of each object you decide to use as a dielectric. And ideally, these are non-conductive because if it's conductive, it can mess up the E field. Now our final example is with the coax, and in order to find the capacitance of a coax, it is usually per unit length because you're given coax wires as a wire itself, 5 meters, 6 meters. And so in order to find the capacitance, you find it on average per unit length. But you still start off with this basic relationship. And it's helpful to draw it out because a coax is just a piece of metal like this, conductive, surrounded by this shell that is also conductive. So there's going to be an E field between those two. In order to find this E field, we have to use Gauss's law. And what would our Gaussian surface be in this case would be a cylinder to match the actual object itself. But we find that the flux really only goes through the 2 pi r portion of that cylinder. So using Gauss's law, we find that the electric field is equal to Q over 2 pi r times the permittivity. So now that we have that, we have to find our voltage next. And our voltage is, once again, the integral of the electric field over a distance. In this case, we defined our distance, a to b, because we were given per unit length. And in this integral, we kick out all of our constants outside of the integral and is just left with 1 over r times dr. And that integral is the natural log of the bounds, which is b over a in this case, times our constants from earlier. And to finish it all off, you plug it back into that original equation, q's cancel, and you end up with the capacitance of a coaxial cable being 2 pi times the permittivity divided by the natural log of b over a. And that concludes the Undergraduate's Guide to Capacitance. Thank you so much for watching.